Hi guys, thanks for coming. Yeah, we have a pretty consistent crowd here, and well, so today I'm gonna finish what I left with last time. So I'm gonna talk about the duality theory and give a preview on the KKT conditions and give examples for them. And after that, I expect we'll still have like 20 minutes time, and I'll cover selected questions, homework questions for that you have just submitted. Yeah, for the six that all of you are going to grade other people's work. Yeah, for those who just came in, I'm gonna cover duality, KKT conditions, and give examples, and also probably talking about the homework questions. We'll have a show of hands which question I'm going to talk about later. So yeah, one thing to note is that I'm also going to give an example of how to use dual certificate to prove things, which is a really useful technique that can come quite handy when you are dealing with new problems, like in compressive sensing when you are doing sparse recovery with L1 norm. And these kind of techniques come up all the time. So so let's start with the primal and dual optimization programs that Suvert has covered in lecture yesterday. So the primal program in its canonical form is we minimize a convex function fx over x subject to some inequality constraints. And also some equality constraint. The corresponding dual, as we have derived in the lecture, is to maximize over the UV, which are the dual variables of some function we call g, subject to u greater than 0. So this is a primal and dual in canonical form. And the definition of G is like this. It is an infimum over all the x. And we have a Lagrangian function here that is just a primal plus the dual variable transpose hx plus v transpose lx. So this is the so-called Lagrangian. The reason why we will have a constraint here, the u greater than 0, will come very clearly when we look at the duality. So now what I'm going to do is to first show you why this thing is a lower bound of fx, and also the lower bound of the optimal value of fx. So we have u that is greater than 0, and we have hx to be smaller than 0. Can you see the blackboard? Okay. So we know that this u transpose hx will always be negative. Will always be smaller than or equal to 0. And also for all the feasible solutions, here Lx should be 0 according to the primal constraints. So So for all the feasible solutions of x and feasible solutions of u, the GUV should always be a lower bound of fx. And will always be smaller than f star x, smaller than f x. And this f star as x, I use it to denote the optimal values, optimal objective value of the primal. And we also know that this GUV is anything that is here, that is a dual objective function. So by the optimality of the dual, we also have an inequality that is for GUV, it is smaller or equals to G star UV. So if we concatenate these inequalities all together, what we will get is GUV smaller than G star UV small. Yeah, let's write it in another way. Suppose we have a feasible solution that actually attains G. This equals to, by the definition of G, this equals to the inf over all x belonging to Rn, the L of the Lagrangian x. This is just by the definition of G, the function G. So restricted on the solution U star and V star, we can take the inf over all the x belonging to R. Note that this is not a feasible solution of feasible solution set over there, but it contains all the x that belong to the primal feasible set. That is the reason why we will have this thing. It is further smaller than the inf over x belonging to the feasible set. I use this calligraphic x to represent the feasible set over there. It's a convex set. This inf is also over x. And by the argument we have on here, and by the argument that this is feasible and also hx being feasible, that it is smaller than 0, we know that this is also a lower bound of the optimal objective value fx. Then it is small because it's optimal. It is smaller than any other x. So what I claim is that this chain of inequalities, informally, it captures all we need to understand for duality theory. Suppose we have strong duality. That means the dual optimal value is exactly the same as the primal optimal value. Then we need these inequalities to be exactly the equality sign. Is that making sense? Okay. Somebody's teaching linear algebra here just now. So this gives us a very handy way of writing out the KKT conditions, which the first condition is stationarity. It says that that 0 is 0 is belonging to the subgradient of the Lagrangian when at the point where x, u, and v attains x star, u star, and v star. This is this subgradient is a set that support the function L at this very point. So if L is differentiable at this point, then this simply becomes gradient. This belonging to the set sign will just be the equality sign. And the second condition in the KKT condition will be the so-called complementary slackness. This is simply by the fact that at optimality we need this inequality to be equality. So that means that we need this term in the Lagrangian to be exactly equals to 0 instead of being smaller than 0. The reason why it's complementary slackness is either one of these needs to be 0, because this is always greater than 0 and this is always smaller than 0 for all feasible x. So if either one of these are actually 0, then we will have the equality here. And the first condition actually corresponds to, in an informal way, to the inequality sign here. If the Slater condition verifies, then this condition makes this inequality equality. And the third condition of KKT condition is trivial. It simply says the primal and dual feasibility. So we need to double check that the candidate solution x, u star, and v star are essentially feasible solutions of both the primal and dual optimization. Okay, now let's get on to the examples of how to actually derive the dual optimization. As Silver promised in class that we will do that, and after that we'll have one or two examples on how to use KKT conditions. So you first need to when you have a problem, you usually only have the primal form. So the first thing you need to do is to derive the dual. And then after you have the dual, the next thing you need to do is to check what are the properties that are satisfied by the optimal solution of the primal and dual optimization program. So let's start by deriving duals. I have many examples here. Let's see. Before I go to examples, are there any questions on the derivation here? Okay, then. So example 1, entropy minimization. So the minimization of the negative entropy or maximization of the entropy can be written in this form. Minimize of x, I equals 1 to n, xi log xi. Yeah, I'll leave you guys to verify that this is actually a convex function, and we make it more complicated by adding an inequality constraint and also an equality affine constraint that makes the sum of x to be equal to 1. So this is our primal. Looking at it, because of the constraints, there are no intuitive way of solving this problem except finding the gradient and then do the projected gradient kind of update. But that is not that is not a trivial thing to do because the projection to this convex set may not be easy to do. So the idea goes that why don't we try to solve the dual optimization, since this is the it's likely that strong duality hold for this problem, and it's very easy to verify that by Slater's condition. So let's just derive the dual, and we'll just follow the most easy way of doing that by first writing the Lagrangian. That is and I'll have like two additional terms here. I'll call them the dual variables u and v, or sometimes it is called Lagrange multipliers. V is just u is a vector and v is just a scalar because this is just one single equation and that is a vector inequality. So I don't think I don't know if you can see this, but yeah, this is a Lagrangian, and if we want to derive the dual objective function g, it is the inf of this Lagrangian over all the x. And in order to do that, we take derivatives. We take derivatives of each xi, and then solve for that xi, then plug it back into the Lagrangian, then we get the g. Because the form is very is differentiable, and we can compute that exactly. Instead of solving the differential calculus, I'll just write the final form of g here. So it turns out that everything cancels out pretty nicely, and the g will look like b minus v minus like that. And this is differentiable, and it is it looks somewhat bizarre, but it is differentiable, and this is very easy to deal with. Then the final the dual optimization problem becomes to maximize this function GUV over U and V subject to only U greater than 0. So now we obtain an optimization program where the objective function is differentiable, and we have a trivial constraint so that we can project it very easily to this convex set by simply setting all the negative part of the U to be 0. So projective gradient will work trivially here. So let's get to some more interesting example by how to accelerate the process of deriving the dual by using the Fincher conjugate. So Fincher conjugate, or sometimes called Fincher dual, is just to write the function, the conjugate of f equals to the sup of inner product x and y minus f y. So this is a definition of Fincher conjugate, and it has a very nice looking form that echoes the Lagrangian. That we often write here. So this is an inner product, and this can be considered f. So intuitively, this can be used if we know a function's Finch conjugate. This can be used to compute the dual objective function much faster than as if we take the trouble of solving the differential calculus. So let's see which example I want to cover. Let's just do lasso since everybody loves lasso. So the unconstrained version of lasso minimizes this function. This is just a L2 norm plus lambda. This is a 1 norm because we want to induce the sparsity in the representer x. But now we have one problem. This is a, well, unconstrained optimization. In order to write a Laplacian, in order to write a Lagrangian, we need to add a dual variable here. So what we do? So the common trick of this is to rewrite the primal objective into a constraint form and then adopt the same technique. So let's call the dummy variable e. Let it to be just y minus ax, right? So this is the noise and noise of the fit. So with this change of variable, we can minimize both x and e. So these two are the same. And then plus lambda x 1 norm subject to that y equals to ax plus e. So now we have a constraint form of lasso. So to derive its dual, now it becomes trivial to write out the Lagrangian. It is simply this. And we have a dual variable u, and we put a constraint here. Yeah, there's a lambda. Thanks. So GU is equals to the inf of L over all the x. What is that? It is simply the inf of let's look at it this way. First of all, let's multiply this U transpose into the bracket and expand this term. And this U transpose this U transpose Y is not a function of X and E at all. So we can just extract it out, U transpose E, and then plus the inf of all the other things. But let us write it this way. Since this term involves only x and the other term involves only e, so we can inf all the x, and this term becomes u inner a transpose u transpose x, right? Yeah, let's also do this. We add a minus sign and invert all the terms in it, and instead of using inf, we take the supremum so that it gives us the Fincher conjugate form. And now it becomes a minus. Minus what? It's a minus of lambda x 1 norm. And again, for the other term, we will also just make it the same form as Fincher conjugate, and this is sup over E. U transpose E minus half. But wait a minute, because of Fincher conjugate, we know that the Fincher conjugate of 1 norm is simply the infinity norm. The indicator function to
Should you I think that U transpose E at the beginning is redundant.
That's why, sorry. Yeah, that's why. I had a typo there. Yeah. So this reduces to U transpose Y. What is that? That gives us an indicator function which when U is in the set, it gives you 0. When U is not in the set, it gives you infinity. So and what is this Y here? This Y here is simply the AU together. Then we have the A transpose U. It's infinity norm. That is a dual norm of 1 norm to be smaller, equal to lambda. This is an indicator function, and it gives you negative infinity. And bear in mind that we are maximizing this G in the dual optimization. So if this thing gives you negative infinity, then we can simply write it as a constraint. So that, yeah. And what is the other term? We know that the dual norm of this function is simply itself. And we can very easily verify this by taking the derivative of this and compute the sup. But it's also useful to just remember this. So it becomes minus half U transpose U. And this equals to, this simply equals to this. These two are the same. So now we can write the dual optimization that is very simple. This is a dual of lasso. Minus subject to A transpose U, infinity norm smaller than lambda. Okay. You may ask that does it matter if we change the change of variable into something else? We basically add a dummy constraints into the primal problem by taking E equals to Y minus AX. There are certainly many other ways of doing that, and it doesn't necessarily lead to the same dual optimization. And the dual may look very different, but typically they are still, well, equivalent in a certain sense to each other. And sometimes when you are not sure what to do when you have an unconstrained problem, it makes sense to consider all the choices of adding the dummy variable you have and solve for them all, and then compare which dual has the best form and most easily solvable.
Why is that infinity now?
Where is that the infinity?
A transpose U transpose X minus lambda X L1. Because X does not have a constraint that it should lie between this, should be the L1 should be less than 1. Because for it to be a dual norm, right, the norm should be less than 1 on the X1, right?
This is not a dual norm. I'm using the property that the Fincher conjugate of a norm, when fx equals to a norm, the Fincher conjugate of that is simply the indicator function of its dual norm, smaller than 1. that's a property I used.
So you never.
Is it making sense?
So you never use this fact that x L1
That
is less than.
yeah, that is something you use when you derive the dual norm. But here it is not a dual norm; it's a Finch conjugate.
So you're not doing that here.
I'm not doing the dual norm here. I'm deriving the dual optimization of Lasso. Did we have a derivation of the dual norm in the question? No.
No, I'm just asking. Like I know that dual norm of this would be infinity.
Yeah. So basically, what I'm saying is that
I see what you're saying. You're saying that when you do the Finch conjugate.
Yeah. Yeah.
You get an indicator function, right?
Yeah. When I do Finch conjugate, it gives an indicator function, and that indicator function here, I rewrite it in the constraint because if this integrator function is not satisfied, it gives you negative infinity. So it's like it minimizes this GU, but we are maximizing the GU over all the set of U. So it is equivalent to if we put the indicator function, the constraint here in the subject to part of the optimization. Thanks for asking. Now let's look at something more sophisticated. Let's look at the so-called matrix compressive sensing and try to derive its dual. It's very simple. It uses the same Finch conjugate and the dual norm argument here. Let's suppose X is a matrix. And we also have a E that has the same dimension. And the matrix compressive sensing is it's written like this. We assume as X is low rank, and so we are minimizing the nuclear norm of X plus the one norm of E, because we assume E is sparse. So this is like a classical low rank and sparse decomposition kind of task. Also, this is subject to some linear constraint where we have the operator A that can be simply a matrix multiplication, but we don't restrict ourselves to that. This is like the sensing matrix where we are given a matrix X, and this sensing matrix will compress the input to a much shorter dimensional measurement that is B. And well, sorry, this E is not a matrix. This E is a vector, and so this is a vector one norm. So this is a sensing operator that has an input as a matrix X, and it has an output B. And say if the X has n is n by n, it has n squared entries. But we don't want to store them all. We only need to store a compressed copy of that. And also we assume that this part is corrupted somehow by some external forces with E. So our observation here, this beta is a corrupted version of the original mapping AX. Say if we transmit a signal over a channel, and this can often happen that the bits got toggled from 0 to 1 or from 1 to 0. But hopefully the toggle of bits is sparse. That's why we assume E is sparse.
You said A is not linear?
A is a linear operator.
This is like dictionary learning, right?
Yeah, similar. It's similar to that, but this is called matrix compressive sensing, because we are compressing the matrix X into B, and it's also corrupted. So it's like recovering a corrupted signal B that we observed, and in order to obtain the original signal X.
It might be foolish, but why do we minimize over the dual norm?
This is a nuclear norm instead of the dual norm.
Okay.
Yeah. Yeah, the terminology is slightly confusing here. Yeah, but this is a nuclear norm.
Okay.
And we know the dual norm of the nuclear norm is an operator norm.
Okay.
So let's just write how we derive the dual. Because we only have a constraint here, so we have only one like dual variable, and this dual variable is inf over x and e. Plus, yeah, there can be a lambda here, but I just ignore it. And by applying the same trick, we can extract the term that is not relevant to x and e out first, and then invert the sign. So now we have a max or sup, whatever. This is a joint operator of A. For operators, we have like this is U A X. This equals to A adjoint U X. This is just similar to the matrix transpose. If A is a matrix multiplication, this is simply a transpose. Minus x nuclear norm. And then I have another thing, maximize over E. What is that? It's negative U E minus 1 norm. So again, we can simply apply the Fincher conjugate and get a closed form solution for that and for that. And because the functions are both like norm, this is going to give us two indicator functions. And the two indicator functions, we can write them as constraint. So the dual optimization is to maximize simply U transpose B subject to A adjoint U. This is a matrix, and this operator norm is smaller than 1, and also negative U and U doesn't matter. So I write the 1 norm's dual norm is infinity norm is smaller than 1. If this has a lambda, then we replace the 1 by lambda here. So now we have achieved a completely non-trivial step of deriving the dual for matrix compressive sensing. And the next step of showing that it actually works, meaning that observing B and a sparse E and using the optimization to solve this will give us exactly the true X that got input to this operator. Is simply by providing a dual, like a dual certificate. And it involves some really hard calculations over there, but this is the most important step in order to prove the result. So I'm going to skip the next example, that is to show you that if we find the dual of an identical representation of the same primal objective function, and we by changing it slightly, but it's still equivalent, we will have very different dual. I'll just write out the form here so that you can work You can work it out yourself later. So it's just a norm approximation. Say we are minimizing x. And this can be reformulated into 1 by doing a change of variable. Till we can minimize the square of y instead. Yeah, just check that these two representations are essentially the same, since we are minimizing the norm of y. But it turns out that the dual of the second one is much easier to solve compared to the first one. So that's the reason why, say in Lasso, people usually have a square term on the norm here. So I'll leave it to you guys to work on this out yourself afterwards. So now I'm gonna give 2 examples on KKT conditions. So why do we need it? Why do we bother to write out the KKT conditions? The reason number 1 is that with KKT conditions, sometimes we don't even need to solve an optimization. We will have a closed form solution. Say, consider this QP. Note that this P is a positive semi-definite matrix, so this QP is well convex. And to make things more complicated, we add equality constraint here. Without looking at the KKT condition, we might think of something like projective gradient or gradient descent to solve this problem. But if we just write out the KKT condition listed over there, it's going to be very easy to solve this by a simple linear system of equations. So the Lagrangian, again, the Lagrangian of this thing is half x px plus q transpose x. I ignore r because it's just a constant, and this v is a dual variable, right? So the first condition, stationarity of the KKT condition, requires that if we take the derivative of this L, this Lagrangian, with respect to x, and also with respect to v, we need to assign the gradient to be 0. So making it, taking the derivative with respect to x gives us a simple equation that is px plus q plus a transpose v, and this thing needs to be 0. For the second condition, we need that is even simpler. It actually just gives you the ax equals to ax minus b, and that needs to be equal to 0. So these two together, note that this is simply this also makes the primal feasibility satisfied, and we don't need to care about dual feasibility since this is equality constraint. There's no this u greater than 0 constraint. So that's all we need, and we can rewrite these two systems of equations into a matrix form that is P A transpose A 0 x v equals to negative q and b. And this is a linear system equations, and they can be solved by, say, backslash in the MATLAB. Again, one other comment is that this procedure is used in the Newton method. Suppose we do not have a QP, but instead we have a fx here. And this fx is second order differentiable, is continuous. Then we can take its Taylor series expansion, and that will look exactly like this QP form. Then we can iteratively solve that quadratic approximation of the fx subject to the equality constraint by solving the linear system of equations, then solve it until it converge, and that will give us the Newton algorithm for constraint optimization. Yes. Oh, I'm being sloppy. So just now we demonstrated that we minimize a quadratic objective function subject to a linear constraint, and this can be solved by a simple linear system of equations. What I'm saying is that suppose we have a general function instead of general convex function to minimize instead of this. We can write the Taylor series of expansion for that function. And it will give us this form. And this is a second order term, and this is a first order term, and this is like simply the evaluation of the function at a previous point. So by doing that, we come up with an iterative algorithm that solves the system of linear equations in every iteration. And that gives us the Newton method for solving minimize fx for doubly differentiable x subject to ax equals to b. Is that making sense?
Yeah, and may I ask you how fast it converges?
It converges really fast. I suggest you look at the lecture slides of the last semester's course, convex optimization. They have a very extensive session discussing the Newton method and its variations. And this also leads to the so-called interior point method.
By very fast, you mean a small number of iterations?
Small number of iterations.
Each iteration will be really expensive.
Yes, yes. You need to solve a linear system of equations, and if you do not have any like structures in the system of equations, then it's gonna take n cubed to solve it.
Also, I don't think every Taylor expansion for every function would work, because
I said it has to be doubly differentiable and continuous.
Even in that case, if it's an exponential family, I don't think Taylor expansion would work.
Yeah, it only works for specific cases.
Yeah.
For that, you definitely, if you are interested in that, you definitely need to check out the lecture notes or other write-ups. So I should leave the KKT condition here. I'll leave the KKT condition on top, and I'm gonna give one more example on how to use the so-called dual certificate to prove that the compressive sensing result that of L1 support recovery by using the so-called, you definitely have heard this term, restricted isometry property, RIP. There we go. By the way, we only have time for one of these. Would you rather I go through one homework question, or I go through this dual certificate argument. Okay, yeah, we'll upload the homework solutions to the course website as soon as possible, yeah, before the grading start. So this is a second reason why we need KKT condition. Suppose we are given an X star. How do we know that this is an optimal solution to the primal optimization program or not? One silly thing to do is to compare the fx star against any other fx for any x belonging to the feasible region. This is a way to do, but it's gonna take forever since we cannot check if x is continuous space. We cannot check for every x. So what we do? Using KKT condition is a definite way to go, and is probably a better way than simply doing this. So, of course, the first thing we need to do is to still write out the dual optimization. And when we have it, we have this theorem. Suppose we can construct the dual variable v star such that this v star is feasible. This is the dual feasible set, and also the fx star equals to gv star. This basically says that if the duality gap vanishes for this v star that we constructed, then x star is up. Then x star is optimal. So it's like a trivial argument of KKT condition, since the duality gap vanishes, it's equivalent to the long chain of inequality having everything to be equal sign, and this and the point that x star is feasible. These are just the primal and dual feasibility condition. So how do we use this in practice? The example is again compressive sensing. This time we consider, instead of the matrix compressive sensing, we consider the more classic form of it. So x is a vector, and the task is to minimize the L0 norm of x subject to some sensing matrix times x equals to b, and this b is a compressed signal. Let's assume there are no corrections in here to keep it simple. And the folks in compressive sensing, what they did is that they relaxed this into the L1 norm and solved the convex optimization. And the dual of that, very similar to the dual of Lasso, it looks like maximize the B transpose U subject to A transpose U infinity norm smaller than 1. Yeah, this is a primal, this is a dual. And let's just check the two conditions, the feasibility and the vanishing of the duality gap. So let's see what we can get from there. Okay, before going to that, let's see we have a candidate solution x star. that is the original signal. This X star is supported on the indices set I, let's say. This means that X star I is non-zero, but Xi complement, X star complement equals to 0. Well, having that, we can write an explicit form of this gap equals to 0. That's basically X1 norm equals to B transpose U. But B, by the primal feasibility, is simply AX, and that gives us X transpose A transpose U, right? And because we know that X is only supported on the indices set I, so we can rewrite this equation into, because everything else is 0, so the 1 norm do not have any contributions from the set I complement. Then we can rewrite this to be Xi 1 norm equals to Xi transpose times A transpose U of I. So this is just the inner product of X and A transpose U. And what we did is that we restricted the inner product on just the supported set of X. But just verify that when that is true, that these two are exactly equivalent. And having that, we can solve for U just from these equations. And U has to satisfy. In particular, this A transpose UI has to satisfy the property that is A transpose UI must equals to the sign of Xi. Is that making sense to you? If this do not if this whole thing do not is not equal to the sign of Xi, then it doesn't give me the equality constraint here. So I argue that for the set I, for the support set I of A transpose U, this is simply the sign of X if I want this equality to be satisfied. Is that making sense? Okay. So that's one. And the second thing we need to verify is feasibility. So the dual feasibility requires A transpose U's infinity norm to be smaller than 1. That's basically say all the coordinate, the absolute value of all the coordinates of A transpose U must be smaller than 1. And check that for the support set in I, this is already satisfied. So the condition becomes A transpose U on the I complement must be smaller than or equals to 1. So these two are the only two conditions that we need to verify in order to argue that this X star is the optimal solution to the primal minimization. Well, in order to construct and the procedure to construct this U such that it satisfies these two conditions, and hence certify this X star is the optimal solution, is by the paper called Decoding by Linear Programming, is to make use of the property they call the restricted isometry property of matrix A, and construct an infinite sequence and takes n goes to infinity, and the limit point of this U will satisfy these two conditions. And check that this is the original problem we want to solve. And suppose we know that we have an X that satisfy this thing, and we call it X star. Then what we actually do is to solve a tractable convex optimization instead of minimizing the L0 norm that is combinatorial and NP hard. But suppose A satisfies the condition called RIP, then this minimization, just by taking the trouble of working this all out and constructing this dual certificate, we are able to prove that this X star that is the solution of that is also the solution of that. So I'm running out of time, so I can't go into the technical details. And it's very troublesome how they construct this U. But if you are interested, this is the key idea of the paper, the highly cited paper, Decoding by LP, by Emmanuel Candice. I think he's the sole author of that. So this is more of a proof technique thing. But the construction of dual certificate is usually non-trivial. But we have already achieved half our goal when we obtain the two conditions here, two optimality conditions here and there. The rest is to construct a dual certificate to certify these two conditions. And usually we will require some type of condition in order to verify this. And that's how they derive the RIP condition, which is the most important property of compressive sensing. So I will be happy to talk to you more about it if you are really interested in this line of work. So yeah, that's all.